works. And there were some problems that were held over. Okay, and what we have in the case of number 92, okay, and we have an equation that is quadratic in form, and here, okay, we have 3 times d to the 2/3 minus d to the 1/3 minus 4 is equal to 0. And for what we have here, now we have an equation that is quadratic in form, and again, for an equation that is quadratic in form, if there are 2 variable terms that appear in the letter we are solving for, then the higher degree term will be twice the degree of the lower degree term. Okay, so you have with 2/3 to 1/3, you have like a 2-to-1 ratio. And so we could say, in fact, we can say that this equation is going to be quadratic in d to the 1/3. And I can factor out this equation because I had the right coefficients, where I have this term in d to the 2/3 to be factored in terms along the lines of d to the 1/3. And let me give you just a bit of a parallel. Okay, if you have a trinomial, okay, see we have 3x squared minus x minus 4 is equal to 0. Now you can factor this trinomial. You could do stuff like factoring by grouping or using trial and error. Now for 3x squared, this will go to x and x, and the factors, again, this can be discovered upon factoring by grouping, or again just kind of guessing the right combinations for what we have in the binomials. And your combination would be 3x plus 1 and x minus 4. So again, you have 3x times x is 3x squared. And okay, and you can go back and check. Oh, my bad. See, this is testing. Okay, I got the minus 4 and the plus 1 wrong. Okay, so you have 3x minus 4 and x plus 1. So you got 3x squared, and we have plus 3x and minus 4x for the outside and the inside products. So you have 3x minus 4x becomes negative x, and negative 4 times 1 is negative 4. Now, I'm not working with x squared and x. Instead, I'm working with d to the 2/3 and d to the 1/3. And notice we had the same coefficients with 3, negative 1, and negative 4. And for what we have as on a parallel note, okay, so you have like with 3d to the 2/3, okay, this is 3x squared goes to 3x and x. I'm going to take 3d to the 2/3 and with d to the 2/3, I'm going to factor out what this equation is quadratic in. So I have 3 times d to the 1/3 and d to the 1/3, okay, and for again minus 4 and negative 4 and plus 1, okay. And we can go back and just sort of check for the consistency. Yeah, 3d to the 1/3 times d to the 1/3, and that will be 3d to the 2/3. Okay, so again, adding the exponents together, we have 3d to the 2/3. Outside product, we have a 3d to the 1/3 and minus 4d to the 1/3, so we have a negative d to the 1/3. And the last product, okay, we have at negative 4. And so we have, again, so we have is equal to 0. And now, looking at what we have now, okay, so I've got the factors, and I can set each of these to 0, so I can utilize the zero product property. Okay, so I have 3 times d to the 1/3 minus 4 is equal to 0. I have d to the 1/3 plus 1 is equal to 0. And if I look at separating the variable terms apart from the constant, So I'm going to add 4 to both sides of the first equation and deduct 1, okay, from both sides of the second equation. Okay, so we have in the first setup, okay, so you have 3 times d to the 1/3 is equal to 4. And so what, if we go ahead and look at this one, okay, so we have 3 times d to the 1/3 is equal to 4. And if I go ahead and isolate d to the 1/3, just get the letter by itself. So I'm going to divide by 3 on both sides. So this will come down to d to the 1/3 is equal to 4/3. Okay, so now I've gone from the equation quadratic in form to where I have at least in one of the factors. Okay, this comes down to where I have an equation with a non-integer exponent. Now we've got d to the 1/3 is equal to 4/3, and there was that section where we looked at translation between non-integer exponents and radicals, and the type of radical would be defined by the denominator of what we have in the exponent. Okay, so we have for d to the 1/3, okay, that is going to be the cubic root of d. So the cubic root of d is equal to 4/3, and I can free up d, so the cubic root of d equal to 4/3. I can get rid of the radical by taking the exponent that matches the index number of the radical. So to get rid of cubic roots, in this equation I can cube both sides. And for the cubic root of d to the 3rd, so the 3's go out, so you have d for 4/3 to the 3rd. Okay, you got like 4 to the 3rd. 4 times 4 times 4 is 64, and for 3 cubed, okay, you have 3 times 3 is 9 times 3 is 27. Okay, so you have one solution here will be at 64/27. Now for the other factor, upon taking 1 away from both sides, so have d to the 1/3 is equal to -1. So this equation I now have already in terms of d, and if I write as a radical, so I'm going to have the cubic root of d is equal to -1, and taking care of the radical. And so we have cubing both sides. Okay, so the cubic root of d to the 3rd, so this will be at d, and the cube of -1, so you have -1 times itself, so this will be at -1. And so, and let me mention, okay, now before, when I translate from d to the 1/3 to the cubic root of d, okay, notice that this was set equal to a negative constant. And once again, with even root radicals, I do not have to worry about the principal square root rule. The principal square root rule, again, only applies to even root radicals. So you can have an odd root to reduce to a negative, but not in the case of what we have with an even root radical. So we have both of these solutions will fit into the equation. And so we have, with the solutions, again, we have the values where we have positive 64/27 as well as -1. Okay, now for what we have in the case of number 94, and we have for this equation, again, so I'm going from like x to d, and now we have with number 94, okay, I have this equation in terms of the letter n. So I have n to the 1/2, and we have plus 6 times n to the 1/4. I have -16 is equal to 0, and we have for the variable terms in n, so I have 1/2 degree and 1/4 in degree, and 1/2 is going to be twice the value of 1/4. So this particular equation is going to be quadratic in n to the 1/4 and just on a parallel note, okay, so you got your coefficients 1, 6, and -16, and just on a parallel, just in terms of the coefficient setup, okay, if I had like x squared plus 6x minus 16 is equal to 0, and I factor, so we have x squared going to x and x, again for the weight of the factors of -16 such that the sum or difference will be on the plus side at 6. We have more weight on the plus than on the minus, and we have x plus 8 and x minus 2. Now I'm not working with the letter x or even taking any integer power of the variable. Okay, instead I've got this equation in terms where we have it to be quadratic and n to the 1/4. So what am I saying here is that we're saying that for n to the 1/2, okay, this will factor out to what the equation is going to be quadratic in. And so in this case, n to the 1/2, this will factor out to n to the 1/4 times itself. And we have, in terms of the constants, okay, you have again factors -16 whose sum or difference will be at 6, and again, so you have plus 8 and minus 2. So we have two factors, and we can now set up what we have here utilizing the zero product property. So we have here with n to the 1/4 plus 8, I can set this equal to 0, and for n to the 1/4 minus 2, again I can set this equal to 0 and isolating the variable term. And for the first case, okay, if we had this as n to the 1/4 plus 8 equal to 0, and I isolate the n to the 1/4, so I got n to the 1/4 is equal to -8, and translating from non-integer exponent to radical, okay, so n to the 1/4, that is going to be the 4th root of n, and we have this equal to -8. And so here, before we had an odd root radical, and I could set an odd root expression to where it reduces to a negative constant. But for what I have here, now we got an even root radical, and I'm trying to reduce this to a negative. And since I have an even root radical, again, that cannot be reduced to a negative constant. So for this particular portion, okay, you have no solution. And the reason for that part being that we had the principal square root rule, which applies in this situation. And for what we have in the case of n to the 1/4 minus 2 is equal to 0. Okay, so if I add 2 to both sides to isolate n to the 1/4 in this capacity, so I have n to the 1/4, okay, is equal to 2, and then translating from non-integer exponent to radical, so we have the 4th root of n is equal to 2. Okay, and so we have an even root radical, trying to reduce this in terms of a positive numerical value, and that is possible. So there's no violation of the principal square root rule. So go ahead and free up n here, and I can eliminate the radical upon taking both sides and raising to the 4th power. So you have for the 4th root of n to the 4th, okay, that becomes n. And as for 2 to the 4th, okay, this will become 16. So for this equation, okay, we could have initially had up to 2 solutions, but with the violation of the principal square root rule, trying to reduce a radical in terms of a negative constant, okay, I have only one solution that will work out and that will fit. Okay, and that is going to be the value whereupon n is equal to 16. All right, and now looking at what we have along the lines of working with equations that are quadratic in form, and we'll just go back to the variable x. And let's see what we get here, whereupon we say we have x to the fourth plus x squared minus 12 is equal to 0. And also where we have x plus the square root of x minus 12 is equal to 0. So I had the same coefficients with 1, 1, and negative 12, and we have different degrees in x. Okay, so chances are we are going to have most different solutions in the mix. And so for these, let's see what we get for x. Okay, just with these equations, okay, they are quadratic in form. Now again, we have in the first case, okay, we have between the variable terms, we have the higher degree rests at fourth order, second degree we have for the lower order term. So we have a 4 to 2 or 2 to 1 ratio. Okay, so this equation, okay, that is going to be quadratic in x squared. And for x plus the square root of x minus 12, okay, now x is a first order, and now for the square root of x, now the square root of x, if you were to write as a base to a power, this would be x to the 1/2, so you have like a 1 to 1/2 ratio, which still comes out to a 2 to 1 proportion. And so this equation, quadratic in form, and this will be quadratic in terms of the square root of x. And so for x to the fourth, okay, we can factor to what we have the trinomial to be quadratic in. So we have x squared and x squared, and again factors of negative 12 whose sum or difference will be on the plus side at 1. So you have a little bit more weight given to the adding than to the subtracting. So we have a plus 4 and a minus 3. Again, you can always double check. So you have x to the fourth. Negative 3x squared plus 4x squared is going to yield positive x squared. 4 times negative 3. So it's going to be negative 12. And we can go ahead and set up the zero product property, okay, setting each of these factors to 0. All right. So I have here x squared plus 4 is equal to 0, and if I look at isolating the x squared, so we have upon subtracting 4 from both sides, okay, I will have x squared is equal to negative 4. Okay, and now this case, all right, we have going back, okay, to the square root property of equality. Okay, so if I have, like, again, x squared set equal to a constant, we have x equal to plus or minus, okay, the square root of p. Now with x squared equal to negative 4, okay, so going from x to the second to x, and here we have in the complex domain, okay, the p-value is at negative 4, and so we have for x, we have plus or minus, okay, the square root of negative 4, and the square root of 4 is 2, But since we're looking at the square root of -4, again, we're in the complex domain. So while the square root of 4 is 2, that of -4 is going to be at 2i. And so we have two complex additive inverse roots with positive and negative 2i. Now, for what we have in the case of x squared minus 3 is equal to 0. Okay, so we have upon adding 3 to both sides, so we're going to have that x squared is equal to 3. And for what we have here with the square root property of equality, okay, so we have x squared is equal to 3. And going from x squared to x, we have x equal to plus or minus the square root of 3. Okay. And 3, not a perfect square number, so we have a couple of irrational real roots with positive and negative 3. And so we have for the solutions here, okay, we have 2i and negative 2i, as well as the square root of 3 and the negative of the square root of 3. Okay. Now, in what we have with the second item, okay, so this one, again, we have to be quadratic in the square root of x. And writing what we have in factoring, okay, so we have with x, again, you can factor out x as the square root of x times itself. And again, we have the same coefficients, and just as I added 4 and subtracted 3, I can do the same thing here. Alright, and so we have a factor of addition as well as one of subtraction. And if I set each of these factors to 0, okay, so I'm looking at initiating, again, the zero product property. So for what we have with the square root of x plus 4 equal to 0, okay, and once again, isolating the variable term by subtracting 4. So we have that the square root of x is equal to negative 4. And again, just going back, again, we have with the square root of x, remember, we have the square root of x implicitly has an index number of 2. And here we're trying to reduce an even root radical expression to a negative, and so in this particular instance we have a violation once again of the principal square root rule, and so there will be no solution for this part. Now for the square root of x minus 3 is equal to 0. If I'm looking at adding 3 to both sides, okay, so we want to have that the square root of x is equal to 3. Again, so we have 3 is a positive, okay, and an even root radical expression can reduce to a positive constant. So I can follow through and I can square both sides. And so for what we have in the case of the square root of x squared, that goes to x, and 3 squared becomes 9. And so there'll be one solution, and you could sort of do a quick visual check. Like we have an x at 9 and the square root of 9. So you got square root of 9 is 3. 9 plus 3 is 12. In turn, 12 minus 12 is equal to 0. So another couple of cases of what we have with equations that are quadratic in form. Now, in the crossover to the next part that we have in section R8, and this will be going back to what we have with inequalities, and these will be carried on over to absolute value terms. Okay. But just for right now, for inequalities, there's some notations we'll be looking into for probably the rest of the course. And this will be what is regarded as interval notation. And let me give you just some visuals and introductions. Like we have, like if you have an inequality, those are your statements like greater than, less than or equal to, greater than or equal to. And let's say we have an inequality statement. Say if we have x is greater than 2. Now, if you're to look at this from a visual standpoint, I would just kind of construct a bit of a number line here. Okay, so you have with x is greater than 2. I know that in your textbook, okay, the author likes to use for solid points brackets, and for open points or circles in ALEKS, and the author likes to use parentheses. And we'll just use sort of like the ALEKS notation. And we have, now for x is greater than 2, that means 2 is not part of x. Since we have all of x is going to be greater than 2. And in terms of number line graphing, okay, to kind of represent that we're involving 2 but not including 2, we're going to have an open circle, and for x is greater than 2, we're going to have a graph that is going out to the right. Okay, so this will represent values of x greater than 2, and for what's going to be referred to as interval notation. This is what we have with statements that will consist of parentheses and or brackets. And for the interval notation, okay, so we're going past 2, and notice we have with the ray going out to the right, so that means we're going out past 4, perhaps past 5, and never ceasing. And so we can say that it's going non-stop. And we have the upper limit, it's going to be what is regarded as positive infinity. And for the groupings, now 2 is not included, so we have a parenthesis around this. And for infinity, infinity is boundless, like it's never going to come to a stopping point, so that's going to stay in parentheses. Anything that's a stopping point and is included is going to be bracketed. Okay. And where might brackets come in? We have, let's say in the second instance, we can say we have that x is greater than or equal to -1. So greater than or equal to -1, and the equal sign signals, then we have -1 included. So this, what is otherwise an open circle, we have, thanks to the equal sign, -1 to be part of x. And so that will be closed out. And for the rest of the values, okay, they will be greater than -1. So you have another graph or ray heading out to the right. And this time for the interval notation that defines what we have in x in this case. So we're going from, and this time including, -1. And since -1 is included, that is going to be bracketed. And we have going continuously on out to infinity. Okay, so this is a case of what we have with a couple of one direction inequalities. And another case would be where we have, I'm just changing up the direction. Okay, so we can say that we have x is less than 0. Now for x is less than 0. So again, with the less than sign, no equal included. 0 is going to be left out, so we want to have an open circle. Less than 0 means that we have the graph to be going in the opposite direction, where we have going to the left. And in terms of the boundaries, okay, to which the interval notation is going to be expressed. Okay, now we had going continuously to the right, we had heading out to infinity. We're now going continuously to the left. Okay, we have with continuity at the lower end, we have going boundlessly, where at the very minimum, okay, it's going to go infinite, but it's going to be in the negative direction. So the lower limit we have from negative infinity, and we have approaching but not including 0. And 0 is in parentheses. Again, infinities are boundless. And let's say that if we have that x is less than or equal to -4. That's right. Let me duplicate this graph. Let's say we have x is less than or equal to 4. Okay, so for the less than or equal to 4, have a close point. This time we'll have, once again, rest of the values will be less than 4, and so we'll have a ray going continuously to the left. And for the interval notation, again, what you have on the left, you're starting out with the leftmost region. In other words, going from the smallest to the upper limit. So again, we have from the left, okay, just like if you're reading from left to right. Okay, the very minimum we have tending to negative infinity, and the upper limit, okay, where the graph ends up on the far right, okay, we have at 4 and including 4. So we have the 4 is going to be in the brackets. Now let's say that if we have activity running on both sides, okay, let's say we have this set of all real numbers. And some might symbolize this by the capital R. And so what's going to happen here is that for the set of all real numbers, we're going to have running non-stop in both directions. Okay, so you're looking at all the decimals, all the fractions, all the rational numbers, all the irrational numbers, all the integers, all the non-integers, and we have going continuously to both the left and the right. And the interval notation that defines the set of all real numbers will be parentheses surrounding both negative and positive infinity. So anytime you see this with parentheses around positive and negative infinity, okay, that's going to be referencing the set of all real numbers. Okay. And so far we've had infinities involved. And one might ask, okay, could there be such a thing as an inequality, okay, where the interval notation will not have negative or positive infinity? And now such a case would be where you can have what will lead to a compound inequality. And such a case would be where you have like a certain starting point that is finite, and also where you have an upper limit that is also going to have reach a saturation level or saturation point. And let's say if you have like -2 is less than or equal to x is less than 3. Okay, so you have -2 is less than or equal to x. That's like saying that x is greater than or equal to -2. And negative 2 is included thanks to being right next to an inequality that has the equal sign included. Okay, so negative 2 is less than or equal to x, signals that you're going to have a close point on negative 2, and for x is less than 3. Okay, so anything inequality wise that does not have the equal sign signals that we're going to have like an indicator of exclusion, such as an open circle in the graph. And for the values of x, you have between negative 2 included and 3 not quite included. And so for the graph here, instead of a ray or a line that runs continuously, we're going to have what's referred to as a line segment. That's going to connect the solid point on negative 2 and the open circle that resides on 3. Okay, so you don't have any continuity throughout left or right. And for the interval notation on this one, okay, so we're going between negative 2 and 3. And since negative 2 is included, that number is going to be bracketed. And we have 3 is not included thanks to the less than without the equal sign. And so that's going to be in the parentheses. Okay, so we have close at negative 2 and open at 3. Okay. And just for what we have in the case of section R8, and we're going to have what will run parallel to a lot of the equations that are linear we have encountered, but instead of the equal sign, we're going to have like statements like greater than, less than, greater than or equal to, less than or equal to. And from section R8, okay, like we have in number 9, okay, we have just an inequality statement whereupon we have negative 2x minus 5 is greater than 17, and for what we have here for negative 2x minus 5 is greater than 17, just like equations, I'm going to get the variable term by itself. And what I can do here is that I can add 5 to both ends. So the left hand side I have at negative 2x, and to the right I have 17 plus 5, okay, which will be at 22. And as I look at going from negative 2x to x, okay, something you might be encountering for the first time, or something you've not dealt with in quite a while. There is a rule that if you have an inequality and you multiply or divide by a negative, the direction of the inequality is going to change. Okay, so again, okay, so whenever you multiply or divide, not adding or subtracting, but just multiplying or dividing by a negative, okay, so you have the inequality direction to change. All right, so we had our x expression was greater than, but now having divided by a negative, okay, that x expression is going to be less than. So we now have negative 2x over negative 2 becomes x, and 22 divided by negative 2, okay, so this will become negative 11. So this statement translates to x is less than negative 11, and just giving a little bit of a visual. To have like in terms of graphing. I'll just do a bit of a quick sketch here. So for x is less than negative 11. Okay, so negative 11 is not included. And for those values less than negative 11, again, we have the direction on the number line. We'll be heading out to the left. And there's another item, okay, that's referred to as set builder notation. And this is just kind of like a repeated notation of the inequality solution. And for the set builder notation, it's going to have like the braces. Braces are like the grouping symbols to identify a set. And your opening statement is going to be like the set of whatever variable you're solving for. Like this, in this case, a set of all values of x, such that, and we have a vertical slash, and then you just fill in the inequality. Okay, so we have the set of all values of x such that x is less than negative 11. And for what we have in terms of the interval solution, okay, so you have, again, going continuously downward. So the lower limit we have from negative infinity, and again we have approaching but not including negative 11. So we have parentheses throughout. And for what we have from section R8, okay, and again, inequality statements are not limited to just the letter x. And in this one we have t to look at, and in solving for t we have the inequality statement whereupon negative 8t plus 1 is less than 17. So we got that 17 once again. And looking at isolating the variable term, which I have at negative 8t. Okay, so this time I can undo the addition of 1 by subtracting 1 from both sides. So the left hand side, okay, we have at negative 8t, we have is less than 16. And dividing once again by a negative. And this time we are going from less than to greater than. So again, you have this bit of history to repeat. And so for negative 8t divided by negative 8, okay, so this will become t. And t is greater than, okay, and 16 divided by negative 8, so that will be negative 2. So this will be the inequality that defines the solution set to t. In terms of graphing, okay, so like negative 3, negative 2, negative 1, 0, and for t is greater than negative 2, so t is not included, such that t is like equal to negative 2. I meant not t not included, but negative 2 is not included. Okay, so t is greater than negative 2, so I have an open circle on negative 2. Everything else, okay, is going to be greater than, so we have a graph array that will be going continuously out to the right. And for the set builder notation, so you just have the repeat of the inequality statement, and just with the braces. And again, so I'm solving for t. So again, just like I have x vertical slash, well, I'm going to have t vertical slash, where you have like the set of all values t such that, and then we just complete the statement where t is greater than -2. And for the interval solution, okay, so I have going from but not including -2. Again, -2 is excluded, so that will be in the parenthesis. And for array going continuously out to the right, that means that we have t heading on out to infinity. Okay, so again, we have an open interval, okay, whereupon we have parentheses exclusively used for the grouping symbols. And now, okay, so far we've had the statements with the variable on the left hand side of the initial inequality statement. Now in the case of number 14, we're now going to have the letter to the right, okay, and looking at solving what we have for m. Okay, so we're going to have that -14 is going to be less than 3 times the quantity of m minus 7 followed by the addition of 7. Okay, so I have the variable we're solving for to be m, and right now, okay, we have m as part of the binomial m minus 7, and we have the coefficient 3 in front. Okay, and so I can just take care of the parentheses upon distributing 3 over the quantity of m minus 7. So we'll have 3m minus 21, okay, again, have followed by the addition of 7. And gathering the constants on the right. So I'm going to have -14 is less than 3m, and -21 plus 7. Okay, that is going to be a -14. And I'm going to get the variable term by itself. Okay, so I'm going to move the 14 over by adding. And -14 plus 14, okay, so that would be 0. We have that 0 is less than 3m. And get what I have in terms of m. And notice this time around, okay, I'm dividing by a positive as opposed to a negative. When I had divided by negatives, again, you had the sudden change in the inequality's direction. But since I'm not dividing by negative, okay, the direction stays. So we have 0 divided by 3. It's going to be at 0. 3m divided by 3. Okay, that is going to be m. And what we'll do here is that just kind of make this visually friendly where I can set up the graphs and also define the interval. Okay, so you have 0 is less than m. See, like 0 is less than, say like if m is 1, 0 is less than 1, well guess what? The logical equivalent would be like 1 is greater than 0. So just kind of flipping it and maintaining the logical consistency. 0 is less than m, same as m is greater than 0. Okay, so I have with the numbers involved. So for m is greater than 0. Okay, so with the greater than sign, okay, 0 is not included. So I maintain the use of an open circle. And for the greater than, we have an inequality such that whenever you graph from that value, in this case, where we have an open circle, we have a ray that's going to go continuously to the right. And for the set builder solution, okay, again, we're going to have m is greater than 0, but in the formal set notation, we have, again, we have m vertical slash, like set of all values of m such that m is greater than 0. And for the interval notation, okay, so again, we're going past 0 and going continuously on out to infinity. Okay, 0 is excluded, infinity is boundless. Okay, so we have another open interval section. All right, and now for what we have at this part, okay, we're going to have absolute value to also come into the mix for inequality statements. And just now the other week, okay, we looked at absolute value. Let's say last week we looked at absolute value and absolute value equations. Now we have this tying in with inequalities. Okay, so for what we have in the case of absolute value equations and inequalities, now I had utilized, okay, some x and k notations, so I'm just referencing this again. Okay, so we have, like, for non-negative value k, okay, so k could be 0 or higher, like k is greater than or equal to 0. Okay. Again, just going back to what we had with equations. If we have that the absolute value of x is equal to k. See, like if k happened to be 7, well, the numbers with an absolute value of 7 will be those numbers that are 7 units away from 0 on a number line, which would be positive as well as negative 7. Okay, so the absolute value of x is equal to k. Then x is equal to plus or minus k. Okay, so those are the possible values that we have for x, negative or positive k. Now, for what we have in the case of inequalities, if we have that the absolute value of x is less than k, if the absolute value of x is less than k, what I'm going to do here is that upon removing the absolute value sign, okay, we're going to have a compound inequality. Okay, so like we had that. Okay, now two numbers with an absolute value of k will be negative and positive k. And if you have your absolute value inequality to be less than and also less than or equal to the value of k, there's going to be a bit of kind of a squeeze play involving negative and positive k, where we're going to have a compound inequality in terms of the values that will define what we have for x. And this, in this particular case, if the absolute value of x is less than k, we're going to have, upon removal of the absolute value bars, we're going to have the statement that negative k is less than x, which in turn is going to be less than k. And in essence, your interval notation for that which defines x will be parentheses surrounding negative and positive k, where neither negative nor positive k will be included in the set. And heading in the same direction, okay, but this time including k, if we had that the absolute value of x is less than or equal to k, then now you're going to have another compound inequality, but negative k and k will be included, and the compound inequality is going to be written such that we have negative k is less than or equal to x, which in turn will be less than or equal to k and the interval solution in general terms will have brackets enclosing negative and positive k. Okay, so you have these inequalities you have going in the same direction. But now if I change things up, see, if I have that the absolute value of x is greater than k, okay, what's going to happen is that upon removal of the absolute value bars, okay, you're going to have two distinct inequality statements regarding x, and there will be polar opposites in a sense. Okay, so if the absolute value of x is greater than k, think of like, absolute value is distance away from 0. In one capacity, you might be looking at increasingly positive, and at the other end of the spectrum, you might be looking at increasingly negative. So if we have like the absolute value of x, in other words, the distance away from 0 is greater than k number of units, you might have at the lower end that x is going to be less than negative k, increasingly negative, getting farther and farther away from 0 on the minus side. But we have at the extreme end, you might have at the positive end, okay, we're going to have increasing the distance where we have that x is greater than k. And for the interval notation regarding these statements, okay, for x is less than negative k, you see we have from negative infinity approaching but not including negative k. That's at the lower end. You have with the or, you're going to have this symbol, and we have tied in, you have for x is greater than k, so you have the parenthesis around k, and the upper limit we have tending to infinity, so you have parentheses. And for this u symbol, this is going to refer to union of sets or intervals. Then we have, in the case of the other possible inequality concerning absolute value, would be whereupon we have the x is greater than or equal to k. So you have almost the exact same statements, but where in the respective items negative k will be included, as will positive k. So we want to have the x at the lower end is less than or equal to negative k, or it could be that x is greater than or equal to positive k. And for the intervals here, almost a duplication, but just some minor but yet significant details. Okay, so we have less than or equal to negative k. So negative k is included in the first statement. So negative k is going to be in the bracket. And for x is greater than or equal to k, okay, so you have starting from and including k. Again, positive k is in the bracket. And we have running continuously on out to infinity. And in terms of tying in, okay, some of these statements together, okay, now let's say that if we're looking at determining the interval solution for x, now to start out with one here, okay, that's a little bit, yeah, kind of introductory. We'll just say we have that the absolute value of x is less than 3. Okay, so you have the absolute value of x is less than 3. Okay, so in terms of which of the scenarios will be drawn, okay, so you got the absolute value of x by itself and you got less than 3, so your k value is already at 3. So this would be like an application of case number 2. Okay, so if the absolute value of x is less than k, which I had to be at 3, then we have upon removal of the absolute value notation surrounding x, we will have comparing x with the numbers with an absolute value of 3, so those would be negative and positive 3. And so we're going to have that negative 3 is going to be less than x, which in turn is going to be less than 3. Again, just from a graphing perspective, just to give a bit of a rough sketch. So you have negative 3 is less than x is less than 3, so neither negative nor positive 3 will be included. Instead, you're going to have everything else in between. And so we have, in the case of the interval solution, okay, so you have between negative and positive 3. Neither value is included, so we're going to have exclusively the use of parentheses. All right. Now, let's say just change things up a little bit. If I have, let's say, the absolute value of 2x plus 7 is less than or equal to 15. So I got the absolute value of 2x plus 7 is less than or equal to 15. Okay, so I got my absolute value term or expression compared to a constant. So this is like another application of the absolute value of x is less than k. And so your k value is at 15. And so we'll have yet another compound inequality. And this time we'll have negative 15 is less than 2x plus 7 which in turn is going to be less than 15. And upon looking at isolating the variable term in the middle, so I'm going to take 7 away from all portions and combining, so we have negative 15 and negative 7, so we have negative 22 is less than 2x, and 15 minus 7 is 8, and going from 2x to x, so we have division by 2, so I'm going to divide everything out among these three entities with the extreme left, the extreme right, and also with the x term in the middle. Okay, so it had less than or equal to, so this is actually going to be case number 3. There we go. Okay, so we're going to have for our compound inequality. Okay, so you have less than or equal to. Okay, so for negative 22 halves, okay, so we have negative 11. It's less than or equal to x. And we have our 8 divided by 2. Okay, so that is going to be at 4. And just take what we have in terms of a quick graph. Okay, so have negative 11. Again, the centerpiece regarding absolute value is going to be 0, but for the numbers involved, okay, so we have negative 11 is less than or equal to x is less than or equal to 4, where the equal signs, both negative 11 and 4, are included. And so we're going to connect the dots. Okay, so we're going to have a line segment in this case. All right, and so for the interval solution, okay, so I have between negative 11 and positive 4, and with both negative 11 and positive 4 included, now we're going to have brackets to enclose. All right, and just this case for what we have. So just going out in the other direction. And let's say that if I have 2 times the absolute value of x minus 3 followed by the addition of 3 is greater than or equal to 7. Okay, and again, just a reminder, okay, do not treat the absolute value symbols as you would parentheses. So you're not going to distribute 2 over the absolute value of x minus 3. We're just going to isolate x minus 3. Okay, so we got 2 times the absolute value of x minus 3. And upon taking 3 away from both sides, so we have this greater than or equal to 4. And taking care of the 2 upon dividing. Okay, so we'll have the absolute value of x minus 3 is greater than or equal to 4 halves, okay, which will be at 2. Alright, and so we have, in this scenario, we got like the absolute value of x is greater than or equal to k. And so this will be like the last of these situations here, once we get down to this particular stage. And so if the absolute value of the expression is greater than or equal to k, which in this case is going to be 2, what's going to happen to the x minus 3 once it's removed from the absolute value signs? Well, we have at the lower end, okay, we have the x minus 3 is less than or equal to negative 2. Or it could be that x minus 3 is greater than or equal to 3. Alright, so looking at solving for x. Okay, so in the first case, if I add 3 to both sides, okay, so we're going to have that x is less than or equal to 1. And for x minus 3 is greater than or equal to 2, if I add 3 to both sides, this is going to come down to where we have that x is greater than or equal to 5. Okay, so we're going to have the x is less than or equal to 1. or x is greater than or equal to 5. And so just looking at it, what we have from a visual standpoint, okay, so you have the numbers 1 and 5, where the equal signs, both 1 and 5, are included. So you have solid points. But for the activity, okay, we have most different. X is less than or equal to 1, so you have a ray that will go to the left. And for greater than or equal to 5, so we have a close point, and we're going to have a ray that will go continuously out to the right. And finally, we have in terms of the interval solution, we have two separate interval statements. So we have at the one extreme, have those values of x less than 1, so you have between negative infinity, and you have including 1, so you have from negative infinity to 1. 1 is included, so that will be bracketed. And we have from x equals 5, and then you have followed by those values greater than. 5 is included, so this will be in the brackets. And again, that U symbol is going to be union of intervals.